I see the first question there from Dave. Do you have any plan to train an LLM with your writings and make it available to Wolfram language users? Actually, there is already a there is a vector database trained from my writings that is in the data repository, and you can call it from. In fact, I even had in the demo yesterday. I even had an example of that using LLM prompt generator with that index to ask it questions that can be answered from that material. Now, in terms of making a more serious me bot, there is an effort by a person in Australia, I think, to make a thing called Stephen Bot that's trained from a bunch of my public writings and transcripts of live streams that I've done. It also has a voice that sounds like me, and I gather it's pretty good. I'm not always the best consumer of bots of myself, because I think I know myself sort of, I think, pretty well, and so it always doesn't seem quite convincing to me. I will say that I have sort of an interesting situation with respect to this, because I've done so much live streaming and so on that there's 50 million words of transcripts of things I've said that are out there available. And that's really a lot to be able to train a bot. I myself also have a lot more material. I have 3 million emails archived over the last 30-something years. I'm a keeper of a lot of personal analytics data, every keystroke I type and so on. So there's really a lot of training material. And but of public writings and public live streams and so on, that's absolutely trainable on. And it's sort of an interesting question, exactly how one should use that. I think it's kind of a good, hey, you want to ask something, well, maybe my bot can answer that. And maybe it will give a silly answer, in which case, well, then I'll get to answer it myself. But, at least sort of a first round of answers could come from the bot. Let's see, a question here from Andre. What are your thoughts on the recent Nobel Prize in physics? Well, I know that the two people involved, John Hopfield and Jeff Hinton, it's kind of cool that the Nobel Prize folk are trying to help themselves be relevant by sort of getting into the neural net world. It's certainly, particularly Jeff Hinton, has had the interesting position of being the torchbearer for deep learning over the course of many years, where many people, including myself, just were sure it wasn't going to work. And then through his student Alex, begins with a K, don't remember the last name, in 2011, sort of they've been doing deep learning. They've been saying, neural nets are going to work, neural nets are going to work, and then they just got some GPUs, and they had done some training with the ImageNet image database, and they just left it training for a month by mistake. They came back, and at the end of the month, it turned out something nobody had expected. It managed to learn, and nobody knew that if you bash neural nets that hard, they would learn. And that was sort of the big discovery of 2011, and that's sort of been rediscovered multiple times since then. But I think I have to say okay, so some personal history of mine. Back in 1980, I was getting interested in sort of how complexity happens in the world. And I had several models for that I looked at in that regard. One of them was neural nets. And I had certainly studied things, well, I had studied a bunch of things von Neumann had done, like his last book, The Computer and the Brain, which is kind of a neural net story. The thing that, so I was interested in neural nets. I didn't really have a way into them particularly. Then John Hopfield came along, and I was at Caltech at the time. He was at Caltech at the time, and I have this model where you can kind of, have a manageable neural net. Now, I had known some other physicists who were working on neural nets and their analogies to the Ising model and so on. A chap called Gordon Shore, another chap called Caniello, Actually, Caniello, I'd sort of independently known because he worked on gamma matrices, which was an area that I'd been interested in. But anyway, so John Hopfield came out with this model that was a very sort of tractable model of a neural net. And I tried to simulate this thing, and I could never get it to work. And I told John Hopfield this. He said, "Oh, you must have made a mistake." I have no idea whether I made a mistake. I don't know what was happening there. And because what I was interested in was what was the attractor basin really like for this model. You could sort of wire in this result or that result. The question was, what was the boundary between those results like? But anyway, at that time, I knew a whole bunch of people who were sort of bringing neural nets back into focus. They call themselves a parallel distributed processing group. Terry Sinofsky, what's his first name? Rummelhart, and a couple of other people. And Jeff Hinton was one of that group. But Jeff Hinton was the one who really continued on a kind of a make this useful in computing direction rather than on a understand how this is relevant to models of the brain. So it's really an interesting case where there was a long period of dark ages, and I think Jeff Hinton was a matter of luck that this came to fruition in his lifetime, because it might not have done. And it's a question of GPUs getting faster and the chance discovery that you could really sort of grind this thing for long enough and have it learn. I've become quite interested in the history of neural nets because I recently wrote a piece about trying to understand the foundations of machine learning. And one of the things that came out of that effort was that the use of real number weights in neural nets seems to be unnecessary. And that's a big deal in terms of the technology of neural nets. People have taken real number neural nets, done the training in real numbers, and then kind of reduced the precision of the weights after the fact. But the question is, can you do everything in just with bits without using real numbers? And I think the answer is yes. And so then I got to be asking the question, well, why did people think there were real number weights anyway? Because neural nets originated in their modern form in 1943 with a paper by Warren McCulloch and Walter Pitts about basically logical calculus of the nervous system. And their idea was to use kind of the kind of methodology of Whitehead and Russell's Principia Mathematica, where they were sort of constructing from logic everything. Their idea was, let's use constructing from logic as the source for all of human thinking. And they kind of made this calculus that is pretty discrete, didn't really have continuous numbers in it. But yet that was the origin. That was the moment when kind of the philosophy of thinking about thinking merged with the neuroscience of seeing how brains actually work. I could talk more about this history. Maybe I shouldn't do that here, but I've been very curious who introduced real numbers into neural nets. Von Neumann kind of picked up McCulloch and Pitts and started talking about probabilistic automata and sort of slowly merged the McCulloch-Pitts story with Turing machines. McCulloch-Pitts were aware of Turing and referenced him in their paper. But it's been, I think maybe Donald Hebb, who invented a learning rule in 1949, maybe one of the people responsible. But it's strange. Where did the real numbers come from? And then I got to asking the question, well, where did neural nets come from? Who knew that the brain was sort of an electrical device that had a bunch of wires in it effectively? And that led me back to sort of a heroine of things, Ada Lovelace. And I knew from studying her that she had this lovely quote that said she thought that there was no reason that cerebral matter would be any less amenable to mathematics than sidereal matter, celestial mechanics and so on. And that she hoped to bequeath to the generations a calculus of the nervous system. She wrote that in like 1843 or so. And so I've been curious, how did she know that, how did she even think about that? Cerebral matter, et cetera, et cetera, et cetera. And I just learned that was right at the time when Charles Whetstone had been bringing the telegraph to England, and people were talking about the telegraph as the nervous system of the country. So it was already an idea of sort of wires and connections and electricity at that time. And I'm still to decode that the earliest mention that I found of neural network is from 1873 from a chap called Alexander Bain, who was a professor in Aberdeen, a professor of logic in Aberdeen, who wrote a book in which he just states, well, the brain is made of these kind of connections. And he actually has a picture that, amusingly enough, is just the same as that picture that you see of the quintessential neural net picture of the kind of multi-layer perceptron kind of thing. Anyway, I'm on the hunt for what the true origins of these things were. And actually, in 2 days, I get to sort of explore one part of my hunt, because the granddaughter of Warren McCulloch, one of the authors of the McCulloch-Pitts neural net paper, had contacted me a few years ago and said, well, she has all these papers from her grandfather that haven't really been sorted too well, and would I like to look at them? And so in 2 days, I'm going to visit the farmhouse in Connecticut that Warren McCulloch bought 100 years ago, that his granddaughter now has, and his son is also there, who's now 95 years old. And so I get to do a bit of first-hand history and see what I can find in the papers of Warren McCulloch, and trying to understand how he came. I do know a fair amount now about this, and Warren McCulloch himself had sort of started in philosophy and then got involved in neuroscience, and in the 1920s had this idea that there will be psychons, there will be atoms of thought, just as there were atoms of electricity like electrons and so on. And then he'd really done practical neurophysiology for a while. He was working at a psychiatric institution in the Chicago area. And there was a young chap called Walter Pitts, who was 19 years old at the time, who was sort of a Principia Mathematica is me type character, who was sort of into mathematical logic. And he met Warren McCulloch, and together they wrote this paper. I'm not sure that either one of them understood the whole paper, but Walter Pitts was the one who sort of introduced formal methods into kind of the analysis of neural nets. And but I'm still sort of on the hunt for how did they really think about these things, what really happened at that time, and so on. And I'm hoping I'll get a little bit more data in the next couple of days and have a chance to write that story in not too long. All right, let me see other questions. Great to hear from Jim Larkin, user of Mathematica since 1999. That's great, and always wants to learn more things in mathematical and Wolfram language. Yeah, I mean, one of the things about Wolfram language is that, I've been involved in designing basically every feature of it, and I have a pretty good memory, but I have to say that the amount that we have in Wolfram language at this point is beginning to exceed my memory. And there are functions where it's like, oh yeah, I vaguely remember that function, but I don't remember it well enough. And there are things where it's like, oh, now I see that function. Wait a minute, I should be using that more. I'm kind of hoping that LLMs and our code assistant functionality will be really helpful, and that I'll really find myself using that a lot and being re-reminded of functions more than I was expecting. I mean, I think it's kind of like when one used to drive by remembering a route by roads and so on, or maybe using a map, one used the main roads. But then one has GPS, and now one's using all those little side roads, and one's finding all these different paths to get to places. And I kind of hope that with Code Assistant, that will be a thing that we all get to do more with Wolfram language. I mean, I think that my main goal has been to have a consistent design for the whole system, so that once you can connect that piece of a system that you never thought about connecting to that other piece, and that the connection really works. That's been sort of my main life activity for the past 4 decades, is to try and make that happen. Let's see, from Willem Nielsen. How do you see the future of coding interfaces developing in Mathematica? Specifically, are we working on getting LLM-driven autocomplete? Yeah, well, I showed yesterday the new Code Assistant functionality, which hopefully will be out very soon, that is really a bit more large scale than pure auto-completion. I think our existing auto-completion is quite good. and we're adding to it. And, accurate auto-completion that is fast enough that it happens as you type and not stupid in what it provides you, so that most of the time it's really helpful. That's been something that we've been tweaking and carefully polishing for a long time. We have tried using machine learning and now LLMs for that kind of thing for a while. One thing we tried to do for a long time in Wolfram Alpha was guessing unmatched brackets, which brackets should be closed and so on. We systematically have failed to produce good machine learning models that do that. And in fact, our heuristic rules have always outperformed the machine learning models that we built there. And I think, the thing that we learn about LLMs and neural nets is the more context that they have, the better their chance of filling things in a kind of correct human way. And I think just it's just the expression. You don't have the whole story of what the person was trying to do. It's more difficult for them to perform well. But so the things that what I showed yesterday was sort of the inspiration button of the light bulb, where you're in the middle of a sentence of text or in the middle of a piece of code. You press the light bulb button and it will try and tell you how to go on with that, or it will tell you possibilities for what you should type. And that's I think these slightly larger scale autocomplete that really is a better immediate use of kind of LLM technology. But we're certainly, it's a big trade-off for us. When can we get local LLMs? When can we get sort of LLM functionality ground down to the point where we can deliver a local network and we can have fast turnaround and so on, rather than having to go to a server and grind a bunch of GPUs and so on to get results. And I think local LLM is coming fairly soon, and that will be very interesting. It's from a design point of view, it's like, when can we assume a local LLM? I mean, it's kind of like the question, when can we assume that you have a web connection? When can we assume that your display has color and so on? What I've always done in design of Wolfram language is to assume the thing that's the obvious sort of future, and to not really try and pander to the limitations of the present. And that's really stood us in very good stead. And I think we're now, the future that we see is local LLMs, and that's really what we're designing towards. And the things that we see with remote LLMs, server-based LLMs, is merely sort of a stopgap move. But exactly how, so autocomplete, when it knows everything you've done so far, may be pretty interesting. Autocomplete that is really just a peephole of seeing what you're doing, I think we do better with our heuristic rules, which I think we do pretty well with. Let's see. Let's see, Mohammed is asking that kind of live thing of informal history of physics they liked. Can a similar one be made for mathematics? I tried a few years ago. I was actually part of our summer school. I thought I'll give a talk about the history of mathematics. And so I did a completely off the cuff kind of history of mathematics from Babylon to today. And that became a podcast that I think has been quite popular. Although I realized after I'd finished it, oh my gosh, I should have talked about this as well. And I kind of, I threaded through the history. It's the history of mathematics is not completely single-threaded, but is fairly single-threaded. It's more single-threaded than many histories of intellectual histories. I think it's been sort of the progress has been sufficiently sparse that it's been like, this happens, algebra happens, mathematical notation happens, algebra happens, calculus happens. These are sort of separated pieces rather than a lot of threads that you have to kind of track together. Let's see. Ray Preder is asking, what are the most interesting use cases of LLMs that you use more than once? Well, let's see. One that I see every day is we can try and keep track of what's happening with LLMs. And so starting early last year, we've had an automated system that abstracts from LLM papers. And that's a really good use case because, you have to read the different abstracts different authors write. And it's kind of, you have to get into the groove of their way of writing and so on. But if it's an LLM, it's kind of, it's a little bit banal in the way that it writes, but that's good because you tell it, make a 3-sentence abstract of the abstract, and they're all pretty uniform and they're very easy to sort of click through and read through. So that's a good use case that I see a lot. There are, I expect the use case of, I don't remember how to make a table that has alternating background colors on successive columns. Do it. I suspect that will be a really common use case for me, and for many of us, I think. I think the kind of these use cases that involve function approximation and so on. I'll tell you a story about the early history of Mathematica and Wolfram language. Back when I was first starting to design Mathematica, one of the things I wanted to do was to add in all those couple of hundred special functions, and I wanted to, evaluate them to arbitrary precision anywhere in the complex plane. I talked to people who were experts on mathematical function evaluation at that time, and they said, this was probably 1986, 1987, and they said, you're crazy. You just can't do that. You can't get arbitrary precision, evaluation of all these mathematical functions for all parameter values and so on. They said, by the end of the 1990s, it is our goal to have quadruple precision integer order Bessel functions done. And so I was like, well, that's not good enough for me. What are we going to do? So what we did was we invented a methodology, basically a sort of industrial process for finding rational approximations to special functions. And we set a bunch of machines loose for months, just finding these approximations. And in modern times, everybody would call that machine learning. We didn't have that name for it at the time, but that's essentially what we did, was using rational approximations to these functions and deducing those rational approximations, which we can then use to evaluate the functions. Now, an interesting question in today's world is, well, what about neural nets? Those are compositions of functions, more elaborate than rational functions. They're probably good approximations to mathematical functions. Now, and that's something also we've experimented for quite a number of years with PDE solutions along the same lines, still not really quite getting, well, we haven't had really quite the reliability we'd like to see there. I have to say, I did a study a few months ago, sort of under the rubric of can AI solve science, of what happens if you just give a neural net, you train a neural net to even know a sine wave. Does the neural net manage to continue the sine wave successfully? Well, the answer is basically no. The thing basically reverts to its inner nature, whatever its activation function is, and it doesn't manage to make that continuation very well. So so I think sort of it's a complicated thing. When do neural nets, when do they do well? They seem to do well in places where the things that they're doing are things similar to what we humans do. And I think that happens because their architecture is not that different from brains. And I think cases where we're asking to do something different, it's a more complicated story. I was looking at the three-body problem in celestial mechanics, where, they're very complicated trajectories. Whenever the trajectory is complicated, neural nets, at least the way I was using them with transformers and so on, really weren't able to track it. When the behavior was quite simple and you just have this little sort of corkscrew type thing of one, star orbiting the other star, then it did pretty well. Then I compared with what happens when you do protein folding with modern LLM neural nets. And it's sort of the same story. I mean, you see a lot of, the Nobel Prize in chemistry this year went to these folks who were involved in doing this. I have to say, I have to say there were quite a few people who were really involved in that story. Who, prizes are a funky business at the best of times. I like to think that it's not none of them sort of capture the whole story, so to speak. But in fact, one chap, long time Wolfram language user, I think he's been at some of our conferences, Mohammed Al-Qurashi, was a person who back in 2003, he was at our summer school and he said, machine learning is going to solve protein folding. And I said, yeah, okay, maybe, I don't know. And he kept on working on it. And in fact, a bunch of his work was foundational to what became AlphaFold and so on. He's now a professor at Columbia. He's actually written a lot of the commentary on what's happened with AlphaFold. But so that was kind of the early story of machine learning being applied to protein folding. But his main statement about sort of why it works is that really you're matching up sort of these sections of proteins which are already known in the protein data bank. But what really the machine learning is doing is smoothing out the gap, the interfaces between those domains that you kind of know what they do. And so it's really an interpolation type problem in that case. But the thing I noticed is that when you do this protein folding stuff, when you have an alpha helix and it's, you know, nice and regular, then yes, the neural net does pretty well. When it's a complicated globular mess, the neural net does about as badly as it does in the complicated globular mess in the three-body problem. They look remarkably similar. So it's a complicated issue when, you know, it's one thing when neural nets are doing things that are kind of like humans do. It's another when they're trying to do things that have no reason to connect with humans. Well, there is maybe a reason, because if what you want to know is, are the features of a protein that we humans pick out this way or that way, then that again is feeding into kind of the human story. You know, it's I do think that the sort of linguistic user interface that neural nets provide, that's useful, and that's what we're making use of in Code Assistant and so on. And I think there are a bunch of other use cases for that. I mean, you know, just yesterday and day before yesterday, I've been working on a sort of minimal model of biological evolution. It's quite lovely, actually. I should have done it in 1985, but I did not have the right intuition at that time. Really intuition that came from the success of machine learning and the fact that I should just run things longer and then they would work, and they did. And even the things I was running were kind of the same as I was running in 1985, but it didn't take them long enough in those days. But in any case, I've been trying to recognize we've got all these different sort of patterns of behavior of these sort of minimal artificial organisms. And I kind of want to do what a taxonomist would do and sort of classify them into the phyla and the classes and the families and so on. And I was hoping that machine learning could do a good job of that. And so far it was really falling on its face in that effort. And so I think that's I don't know what to make of that, and that's sort of a interesting question whether one can do. In fact, someone quite a number of years ago used Wolfram language to do entomology classification, image classification of beetles, and I think with some considerable degree of success. It's probably a system that's in practical use at this point. So I don't know what to make of all of that. Let's see, JC asks, oh, that must be John Keel, hello, asks, whatever phase of AI we're in, what milestone will tell us that this phase has ended and we're on to the next phase? What will be characteristic of the next phase? You know, the AI story, I've seen it over the course of, I don't know, 45 years or something. It's gone from well, back before I knew about it, everybody thought we'd be able to automate thinking the way we've been able to automate mechanical work with bulldozers and so on. That didn't work out. Then there was kind of it's going to be neural nets. And that was in the early 1960s, things like perceptrons and so on. It's going to be neural nets. Well, that didn't really work out. And then, I mean, I can tell a very detailed history of this, but and the kind of unfair killing of neural nets in the mid-1960s as a result of sort of mathematical analysis of simple cases and saying, well, those don't do anything interesting. And then people kind of lost the herd mentality, said, oh, well, those don't do anything interesting. So by extrapolation, nothing in neural nets does anything interesting. Well, then by the 1980s, really, it was a question of expert systems and kind of rule-based systems. And it was like, they're going to solve everything. They didn't. And then, you know, it's the rebirth of neural nets happened in the beginning of the 2010s, and image processing got image identification got solved. That was a big sort of jump. Image identification hasn't gotten much better since that time. There was another jump with speech to text, another jump in 2022 with text generation and ChatGPT and so on, another jump maybe a year or two earlier with image generation and so on. So there is different modalities that can successfully be tackled. And I think, you know, a modality that's sort of coming is video, and we're just sort of at the beginnings of that modality. Another one is music, where that's been surprisingly difficult, but that looks like it's sort of getting close to being doable. I think there are these different modalities that will get solved. Then there are a lot of sort of thoughts about, well, how can this be used for science? You know, and I think the better hopes are things like mining the literature, so to speak. You know, what is it that sort of is given this literature in this corner over here of, you know, the properties of lithium or something, how does that relate to the properties of boron that was studied by some completely different group? But by being able to sort of see those analogies, by able to do kind of the analog for text of what statistics does for numbers, of sort of giving you these aggregate answers, that's a that's kind of a I think a coming attraction there. And I think I don't know, there'll be some modality jumps. I think that and then the neural net is suddenly going to wake up and be just like us. I just don't think that that's a thing. I think that this kind of the use of, you know, a traditional LLM is just generating a token at a time. Sort of the progress in recent times, which is something that certainly people like me sort of thought would be possible, is not only do you just sort of spit out a token by what's statistically most likely, but you also can look at many different paths of possible sequences of tokens and ask, well, which path do I have to follow to give me the best chance to hit this target in the end? I mean, if I was to make it sound very fancy, I would talk about quantum LLMs, and I would talk about the sort of quantum paths that might be followed and being able to find which path to follow to sort of get to that target. And so that's clearly a thing that's coming in the most recent models, a bunch of work along those lines, and that's producing, you know, nice results. And I don't know kind of what drama there will be from that. But, you know, I think as a practical matter, the, you know, AI in its current form is going to be useful, a lot of linguistic interface capabilities that are definitely useful. You know, the talk to the bot story will be a continuing thing. I think the really important stuff that will come out is all these use cases that use AI in places where it's good and don't use it in places where it's bad. You don't try and solve computational problems with neural nets. You use Wolfram language to solve those and use the neural nets to provide kind of the fuzzy linguistic interface to those things. But I think more and more use cases will be found. For example, our AI tutor project is an example of a fairly elaborate use case where if you look at what's inside that system, it's an awful lot of software engineering and bits of LLMery that are sort of being put in places where it makes sense, along with a lot of software engineering and a lot of content development. And I think that will be sort of a typical thing. What's tricky about LLMs is that unlike kind of traditional software development, where you kind of know what you're getting, with an LLM, you're kind of poking at this wild animal and hoping that it will behave in a certain way. And it's a much less definite kind of thing to know what's going to happen. As a practical matter in the AI industry, I think that you know, a huge investment has been put into it. People still believe that it's a field where you put more money in, you get more money out. And that's a thing that happens occasionally. You know, it happens in, I don't know, video games where you can run more ads and more people play the game and you see a positive feedback loop and you just keep feeding it. So what people have believed right now is you spend more money, you know, you spend your $1 billion to train a model, you'll get more than $1 billion out. When that stops working, that will be one discontinuity. And I'm not sure it's even working now, but I think it is a very bizarre sort of situation that even though we understand so little about the foundations of machine learning, still we're spending billions of dollars training these models. And I think so that's one dynamic. It's also it's a funny thing, sort of where the money is getting made. And, you know, clearly NVIDIA and the hardware folk are making money from sort of the AI story. the LLM manufacturers mostly have not. And, you know, I think the appliers of LLMs will find good business there, and hopefully a lot of people will successfully apply LLMs using the framework that we built in Wolfram language and connecting the LLMs to this kind of computation augmented generation that's possible with Wolfram language. And so, you know, that's a thing in these use cases. You know, I have to say another thing that may happen is we understand very little about why machine learning works. I think it is a fantastic opportunity for people in physics, mathematics, and so on to really go in and see what we can understand. I think a lot we will not be able to understand. I think a lot of it is kind of irreducible computation, sort of a story of limitations from computational irreducibility. I kind of made the analogy yesterday about, you know, you're building a wall and you're building it out of rocks that you find lying around on the ground. Those are your kind of lumps of irreducible computation. And it's something where sort of having an explanatory theory of your wall is really not possible if it came from just a bunch of rocks that were lying around. And so I think the question is, what can we actually talk about? What things will end up being the kind of laws of neural nets? I mean, I thought in the case of LLMs, I was interested beginning of last year in this notion of semantic laws of motion, or laws of semantic motion. You start an LLM going in a certain direction in kind of meaning space, and is there a law of motion that says the rest of that sentence will be completed by going in this direction in meaning space? Now, the fact is that meaning space, despite people's implicit assumption, is really not a very flat space. We don't know what kind of space it is. We don't have a good characterization of it, but it's surely not a flat space where parallel transport works and all those kinds of things. So understanding that and doing the physics of that, I think, is important. I don't know how far we'll be able to get, but there may be sort of some dramatic conclusions about that will sort of reflect on what happens in industry. Certainly my own efforts in trying to see to what extent one can use kind of bitwise machine learning rather than real numbers, you know, that looks like that has a kind of an effect. If you care about, you know, should you concentrate on GPUs that have good floating point arithmetic, or should you build hardware that just does very good bitwise kinds of things? And you know, I think that neural nets and AI, it's a complicated thing for us, because I can see that, you know, we have been in a state of high excitement about AI. Everybody has been in a state of high excitement, and it's sort of, that excitement is in some ways not, you know, some parts of it are justified, some parts of it are not. These things, you know, they gradually deflate. I don't think this one will burst as a bubble. I think it will sort of slowly get closer to reality, although there will be a bunch of failures in companies that sort of overinvested in training and other kinds of things. You know, I think my operational observation is, I was just at some event in Silicon Valley a week or two ago, and I think of the 100 people or so who were there, sort of, I don't know, industry leader type people, probably about 5% of them were true believers, in the sense that they're just like, neural nets will do everything. You feed them computation, they're just going to figure it out. Somehow they're going to figure it out. Maybe 20% were really skeptical. They were like, this is all nonsense. It only does toy things. And the rest were kind of somewhere in the middle. And I think somewhere in the middle is kind of the correct place to be. Let's see. Jim asks, what do you regard as the most significant potential society-wide or existential threat posed by AI? You know, I signed up a week or two's time to have a discussion with a chap called Eliezer Yudkowsky, who is a person who sort of believes that AI will destroy us all, and is of the opinion that unless we stop all AI development now, we'll all definitively die at the hands of the AIs. I think his arguments aren't quite right. I still try to decode quite what his arguments are. I'm sure I'll learn more when I talk to him. But you know, his mostly about sort of that AIs are improving themselves, and eventually the AIs will learn to improve the improvements, and the whole thing will accelerate until we get to the singularity. The idea that we would get to sort of an intelligent singularity, that's an old idea. I remember a chap called Jack Good, who I met years ago, was one of the people who was kind of into the intelligence singularity. I just don't think it works that way, because I think it's kind of like, well, if you think that IQ tests measure everything about humans, well, maybe you think there's a one parameter family of intelligences, but it just isn't really that way. Instead, it's kind of like there's this sort of frontier of irreducible computation, and there are many different sort of pockets and paths of reducibility that let you figure things out from that frontier. And it's not the case then that you can just say, oh, this AI is smarter than that AI. It's not kind of a linear ordering kind of thing. It's something where everybody's kind of working into these different sort of rivers that go into this this land mass of what has to be figured out. So it doesn't really look so much like and then at this moment, sort of the thing will jump to that point on the real line and it'll exceed everything else. I think that, well, the biggest societal issue that I see with kind of decision for society is how much computational irreducibility can society withstand? And so, computational irreducibility is this phenomenon I started talking about 40 years ago now, that just because you know the rules for something doesn't mean you can immediately jump ahead and know what will happen. Instead, you're basically, in many cases, forced to just follow the rule one step at a time to see what will happen. In effect, you have to do the same computation as the system itself. It's an irreducible computation that has to be done. And now, if you want a computational system to do the best it can, then it better be doing irreducible computation. Because if it wasn't, you could kind of compress it and jump ahead a bit. And then why are you having the computer do the computations it's doing? So computational irreducibility, being at the computationally irreducible limit, is letting the computer do as much as it can do. The problem with computational irreducibility is you don't know what it will do. The only way to know what it will do is to actually run it. Well, so if you want to know, I want my AI to do only what I want it to do, only the things that are the right things for it to do and nothing bad, well, then you can't have computational irreducibility. You have to have a computationally reducible system where you can kind of see where the levers go and see what it's going to do. So there's this big choice between controllability, predictability, and capability. So and realistically, we're going to come down on the side of capability. Realistically, it's going to be, even though occasionally we'll have a nasty surprise from what the AIs do, we'll mostly just want the AIs to do what they can do. And that will inevitably lead to a kind of a civilization of AIs, just like there's, the natural world out there doing what it does. There'll be sort of a civilization of AIs where the things that are going on computationally inside are not immediately human understandable. But we have to kind of figure out how to coexist with that. As a practical matter, what's going to happen quickly? I think, there are silly things people can do with AI, and that are just sort of human problems. I think there will be, well, there are things that happen like governments or the European Union just sort of saying, oh, we don't want AI to do anything bad or something, and let's write laws about that. That's kind of hopeless. It's kind of like, we're nearly 100 years since Gödel's theorem, and that together with computational irreducibility and so on basically say those laws are unwritable in a way that people will find useful. So certainly, but that's one sort of thing that can happen. I think as a practical matter, oh gosh, I mean, one thing you can say is let's not worry what the AIs think internally. Let's give AIs full freedom of thought, but let's lock down the actuation layer of AIs. Let's make it so that AIs can only actuate things that aren't going to cause trouble. Well, the problem with that is some of the actuation done with AIs is things like ranking of social media posts. And by ranking social media posts, you can get those crazy humans to do all kinds of things. So we are the actuation layer for a lot of AI. And that's not something you can expect to lock down. It's something where if you give the AIs freedom of thought, so to speak, then the actuation layer is in part humans, which can't be sort of locked down. I mean, you can say, we're just going to have the rule that the self-driving car will never be able to drive off the side of the road, however the road is defined. But much of the actuation comes through sort of human actuation, which is much more difficult to control. But, you know, I'm sure people say one of the near-term things is going to be autonomous weaponized drones. That's one thing that will be sort of a bit of a wake-up call in terms of the sort of killer robot scenario. And I think that's you know, coming real soon, because I think that's a thing where, you know, in drone warfare, which has become, you know, kind of a common thing these days, sort of the big way you disrupt it is by having kind of the, you know, you cut off communications and so on. As soon as you're doing that, you need an autonomous drone. And as soon as you have an autonomous drone, you have an AI that, you know, can shoot at things and so on. And I have to say, you know, I've seen these wonderful demos of sort of the modern firework display, the modern silent firework display of configurations of drones rearranging themselves in the sky and so on. And there's a certain military parade character to what you see there. But so those are a few things that I think will sort of come fairly soon and might surprise people. I mean, I think the real, you know, one question would be, will there be kind of a Sputnik moment for AI? And I think ChatGPT was as close as we're going to get to that in the foreseeable future. Let's see. Andreas asks, what's the plan mid-term with your new and own LLM service? So we have been working on training LLMs. I don't know how long it'll be before we are delivering LLMs for local use. I hope not too long. There may be an intermediate phase where running LLMs on our own hardware. You know, we have tended for Wolfram Cloud and Wolfram Alpha, we have our own data centers and so on. Although those things are runnable in AWS and Azure and so on. But we have been running them ourselves in our own hardware. We're not, we didn't stock up on GPUs, so we're not immediately able to turn all that hardware into LLMs, although I gather GPUs are getting a little bit more easily available. So we probably will be able to do that. It's not clear it's worthwhile, because I think the time when we will need to provide LLMs in a centralized way is probably quite limited. And we'll probably, what we're doing for the code assistant and LLM kit, we're using external cloud services proxied through us. So all of the kind of the, you know, payment and authentication and so on is going through us. And we're dealing with the back end messiness of, well, which cloud are we going to use today and so on. Chris Kenny comments, most impressive work on tabular, thank you. Are you contemplating adding joins and queries as part of evolving this into a homegrown relational database? So yes, is the basic answer to that. And I'm thinking joins we pretty much already have in the functionality that will come out in 14.2, and many kinds of queries as well. So I think we're in pretty good shape in that regard. Now, tabular, sort of part of the idea there is this seamless interface between a tabular where the data is resident in memory and a tabular where the data is in a remote relational database or remote file. And what we'll be delivering in version 14.2 is the local version and relational database version. We have a bunch of file capabilities which will come out later on. Well, this is a more general question from Will. When exploring a scientific question, how do you think about balancing using other research versus figuring out things for yourself? You know, my approach to that personally is that they're things that I'm interested in, and I kind of pay attention sometimes for decades to what's happening in those fields, gradually trying to build up some degree of knowledge and intuition about those fields. Then when I really start diving in, I kind of try and figure it out for myself with the background knowledge that I've learned over the course of sometimes decades. Because I find it much easier to, you know, to sort of, you know, with the tools we have and so on, I find sort of the clarity of thought that we get by just write a piece of Wolfram language code that does that. which is very different from read this paper and try and understand what it's talking about. So I tend to do the just barrel through it myself and try and figure it out for myself. And then maybe if I get stuck, I'll go and say, has anybody figured that out in the literature? But more, I'll just be barreling through it myself. And I think then, typically when I write things, I like to understand the history. I like to understand the history to contextualize, particularly when I've come up with things where it's like, wait a minute, people have believed that the opposite was true for 50 years. Am I really right that about what I'm saying? Well, let me understand the history of why people came to believe the thing they came to believe. And so I've been really keen on understanding that history. And sometimes I do that as sort of a hobby activity as I'm doing the main piece of work on something. And sometimes that comes more towards the end. I have to say, one of the things that's happened to me quite a lot recently is I realized, 100 years ago, a bit more than 100 years ago, was a moment when sort of formalism had first developed. Well, formalism kind of really developed in the 1800s to 1880s and so on. People were kind of formalizing mathematics and other areas. And that was sort of the golden age of formalism. And a lot of things people sort of thought they would formalize in various kinds of ways. They tried to do it. Sometimes it worked, sometimes it didn't work. And I feel like a bunch of projects I'm doing is sort of picking up the pieces from things that didn't work at that time. But now that we have a sort of clearer idea of computational thinking, how to think about things computationally, that those kind of sort of things that, oh yes, we might be able to formalize that, are things that we can now finally pick up. And I've had this sort of strange feeling as I look at things where I'm like doing something and I realize people almost did this 100 years ago, but didn't quite. I feel this kind of strange sense of responsibility that, this thing got lost for 100 years. And now we've kind of found it again. And it's like, we better make it work this time. We don't want it to be lost for another 100 years. Well, Mohammed is commenting, there's more science questions. I heard that time is essentially the application of irreducible computation. What about the application of reducible computations? Do we have philosophical or physical terms to describe that? Yeah, reducible computations are the story of science. Reducible computations are when we find laws of nature, what those laws of nature are ways to take all the irreducible complexity of nature and find some slice of it that we can kind of grab onto with our finite minds and generate a human narrative from. When we look at molecules in a gas bouncing around, we're not trying to describe all these detailed molecular motions. We pick these particular features like the pressure of the gas about which we can make sort of scientific laws and generate kind of a human narrative. And that's the thing that is sort of the story of reducibility. Reducibility is sort of what we can explain. It is what we have traditionally thought of as scientific laws. I think reducibility, one of the things I've been studying recently, I've been interested in the foundations of economics, and this is something I don't really know if this is really going to pan out this way, but there's a question of, is reducibility the main value, the main source of value in the world? That is, the world is doing all these irreducible things, and we make inventions that let us kind of jump ahead and essentially save time by doing things. So we're kind of the sort of the frontier of invention is a frontier of reducibility. By the way, in mathematics, for example, reducibility is sort of the discovery of theorems and lemmas that let us kind of jump from one place in this kind of network of all possible theorems to another. And so those are kind of analogs to that. I think that it's kind of like the story of reducibility is the story of what we understand. And the question of whether we have discovered all the reducibility that we can is we certainly have not. There are, we have particular kinds of reducibility that we, with our particular senses and kind of brain architecture can deal with. There are other slices of reducibility that surely exist, but which are not immediately accessible to us. It's just like in mathematics, there are different forms of abstraction, different sort of slices of abstraction that you can make that reveal different kinds of things. Bruce Colletti asks, any plans to turn Jose Martin Garcia loose to expand group theory? And Bruce is pushing for more group theory. I'm not sure. I mean, I think we've certainly looked at taking some of the crunchy computational group theory that exists in various libraries. There happen to be, we've had long running. This is the joys of open source software. There's a particularly popular group theory software package where the authors of it have said for decades, we'd like you guys to use this stuff. We say, okay, but we need something that says it's okay for us to do that. And they say, well, oops, we don't really know who can sign that piece of paper because we kind of gave it out to the world, but we kind of gave it out to the world with these weird conditions, and we don't really know who gets to sign the piece of paper that says it's okay for you to use it. So that's a rather frustrating situation. But you know, the challenge, I think, for group theory in Wolfram language is not so much a challenge of the algorithms, though there are difficult algorithms. It is more a challenge of the design of the whole thing. I mean, I think that's really the thing that one has to figure out, is how does one get it so that the things, you know, we keep on making progress, like we just been adding, you know, game theory in version 14.2. That's been a long-running design issue. Tabular, a long-running design issue. PDE modeling, again, long-running design issues. It's how do we take this thing and kind of clarify it to the point where it's really usable. I mean, it doesn't work to say we're going to do group theory and we're going to have 1,000 functions to handle all these different detailed weird things in group theory. You've got to have something that's more cognitively kind of coherent than that. And that's been the main bottleneck, I would say. Dave asks, how many CPU cores is it practical to use with Mathematica? The latest Intel and AMD workstations have 128 CPU cores per processor socket. Yeah, well, I mean, I personally, right now, I'm using 228 cores is my typical kind of parallel configuration, works just fine. In fact, in 14.2, the launching of those parallel cores is going to be faster. I have them on many different machines. I think my largest single machine is a 64-core machine. And if you have them on a single machine with shared memory, it's going to be even faster to do things. But yeah, I think that up to, I would guess, the parallel computation system, we're gradually tweaking it, but I'm sort of guessing 500 to 1,000 cores is kind of where it's going to limit right now, because it's still using kind of a controller and subprocess kind of architecture rather than a peer-to-peer kind of architecture in its typical case. But I think you know, 500 you should be safe, and 128 no problem. Now, you know, what's kind of interesting to see when you use parallel table, parallel map, parallelize, and so on, you see it working, and it's pretty good at predicting how long it's going to take to do the computation. Brings up those little blue boxes that show it working. We have done quite a lot of work in the dispatching of computations and essentially measuring how much each processor is, how to partition the problem, how fast each processor is running, and so on, and knowing, you know, what to feed to who, so to speak. That's been fairly successful, and I think, you know, I do this kind of thing all the time. Now, the thing to pay attention to is there is communication overhead, and by the way, the other thing that works pretty nicely is we're pretty good at packaging up sort of all the dependencies so that you just have it running on your local, on your single sort of interactive version, and then you parallelize, you use parallel table, it just works. The only place where that gets complicated is when you're installing something like a file you're using and you haven't specified, you know, when you're using function repository items, things like that, those are automatically cached per processor. That all works nicely. There are some tricks to doing the one kernel per processor per machine, one kernel per machine option for parallel evaluate to let you do kind of an initialization on one kernel per machine where you're storing in a file something. But you know, as I say, the other thing to be aware of is when you're doing parallel computation, you don't want huge amounts of data being sent back and forth. So packaging things up, you're sort of filtering things on the remote parallel end is always worthwhile. But yeah, lots of good. I mean, our parallel computation capabilities have existed for a long time. They've gradually been being polished further but now is the moment when one routinely gets to use them. Gosh, a question from Matt. Do I have a theory of knowledge, and what is our best understanding of what knowledge is? Is it subjective or objective? Boy, I'm not sure I've thought about it in those terms. I mean, I think that you know, there's a question of, is knowledge something that relates to what brains do, or is knowledge something about the state of the world? I think that one of the things that has become clear is knowing abstractly the state of the world, the sort of the ultimate metaphysics, so to speak, is something with our ideas about the Rulliad and so on. It's looking like we have a pretty good insight into what that really is, what the ultimate everything is. But what I think we'd probably fairly consider to be knowledge is something that is really something we can work with in our brains. And that's a much more restricted set of things. That's a tiny slice of the Rulliad that we get to actually think about in our brains. So I think the knowledge for us has to be these things that we get to capture in our brains. Now, what does it look like? What are the things we can capture? A lot of what we manage to capture traditionally is represented by language. I'd like to think that computational language extends the set of things that we can capture and think clearly and formally about, just as mathematical notation and mathematics extends the set of things that we can sort of think formally about. I think the question of sort of, well, what, human language is very floppy. We've tried in computational language, we have a sort of precise language that goes far beyond human language in some directions, but falls short of human language in other directions. We have a project actually very active right now to build what I've long talked about as the symbolic discourse language, which is kind of a symbolic representation of the things that occur in everyday discourse. And that will give us, in a sense, implicitly, sort of a new take on the theory of knowledge. I mean, I view the symbolic discourse language as a project that got started about 2,000 years ago by Aristotle, and he kind of stopped at logic and didn't go any further. Then it got picked up again in the 1600s by Leibniz and Wilkins and people like that, and they got dropped and they kind of gave up, and hasn't really been picked up again. And so we get to pick that up. And now with a lot of help from computational language and some help from LLMs, I think we may have more to say about sort of the emergent theory of knowledge. I will say that when we were building Wolfram Alpha, there was sort of a question of, did we have a theory of knowledge for that? And at that point, I really felt that we wanted to just build practical things and not try and impose kind of top down a theory of knowledge. And that worked pretty well. And we increasingly saw these different sort of silos that we built join up with sort of meta understanding of different kinds of things. Okay. Let's see. Andreas Hafner asks, now that you have symbolic arrays and vectors, can you make a new symbolic neural net backend that is fully Wolfram language? Yes, I think so. I mean, I think that's sort of the direction we're going. We've been a little bit, when we were first building out our neural net capabilities, we sort of thought about doing that. That was plan A. But then it was like, oh, it's got to run efficiently on all these GPUs, and there's all this effort to kind of, do optimizations and so on. We better leverage the things that people have done for that. And that's been important so far. But then increasingly, we're being able to take much higher level symbolic structures and compile them down using our compiler technology and so on to things that can be run at that low level where we're sort of automating that optimization. So I think that becomes more realistic and more interesting. It's a little less interesting because it's kind of like, well, it turns out it doesn't really matter what architecture you use. There are some tweaks and transformers and the way the attention heads work. There's a practical engineering thing, but it's not it doesn't seem like, it seems like it's the kind of thing where you make any old neural net and you bash it hard enough and train it hard enough, it'll learn stuff. And it hasn't been so far, it hasn't been that sort of the key challenge has been really diverse thinking about architectures. But that may change, and then that will become more important. Guy is asking, how far are we from being able to use Core ML for training? One version away, I would say. We will not be able to do it in 14.2, but we should be able to do it in the version after that. We're definitely progressing in that direction. There's just a whole bunch of software engineering to do to make that work. Roy asks, someone argue that traditional formal education has relied a bit too heavily on teaching statistical models of mental representations of the world, presenting those patterns as intelligence. That's an interesting question. I mean, I think, the great challenge, look, education is kind of about knowing what's out there and learning how to think about things. And, the learning how to think about things, it's sort of been interesting for me to see and thinking about teaching computational thinking. How do you do that? Is it really an abstract thing? Is it a thing where you have to really talk about the actualities of different areas of computation? I think the actualities are important, but in the end, it's a strange activity that's closer to teaching philosophy than it is to teaching the mechanical version of teaching math. It's kind of a thing where you're really teaching about how to think about things more so than you're teaching sort of mechanics. So I find that kind of interesting, and I think the mechanism, well, the sort of, but you need to teach sort of how to think computationally about lots of specific things. It's not just a generalized abstract idea. It's like, how do you think about time computationally? How do you think about kind of geography computationally? How do you think about molecules computationally, and so on? And that seems to be the sort of raw material that you need to really build up a good mental model of computational thinking. Let's see, and I think this is actually a continuation from Roy. The emergence of generative AI, what does it suggest about human intelligence and the future of education? Yeah, I mean, I think sort of education has to be about the things that we can't automate. Teaching about things that we can readily automate, it's interesting for a small set of people, but it's like you might as well just leverage that automation and do the things that only we humans can do. And one of the most important things only we humans can do is to figure out what we want to do. And for that, you kind of have to know what's out there, and you have to be able to sort of actually do sort of thinking about things that you haven't thought about before. And, the AIs can do whatever is well-defined, an AI can go off and do. You just say to the AI, do what you feel like. AIs will go off into the computational universe, and they'll just, they'll study every possible program. And most of those programs, we humans will look at them and say, oh, we don't know why we care about that. So really the things that we care about are things we choose as humans. And that's the thing that's worth learning, how to think about those things and how to sort of interface with what is computationally possible. So I think, it's an interesting challenge, how to think, how to teach, how to think. And I think one of the things that is sort of a notable feature is it's not so much about getting the answer given the question. A lot of it is about figuring out the question to ask, which is something that has not traditionally been a major part of education. A major part of education in the last, since education became, sort of public education became widespread 150 years ago, it's been much more sort of this industrial process of given the question, learn the mechanics of how to get an answer, rather than think of what questions you should be asking and so on. So I think those are some directions. I think that it's very interesting, sort of the AI tutor project that we have is a serious effort to see whether we can get an AI to learn enough about us humans that it can teach us well. I'd love to have an AI that if I'm trying to learn about some field, it knows what I know, and it says, well, the thing you need to know that you are confused about is such and such. To be able to identify that thing by having a model of me, and I think that's somewhat realistic, and I think we're sort of implicitly seeing that happening with the AI tutor project, which I think is really, it's really, the demo I did yesterday is actually the longest demo I think I've done of it, ever. And it did really well. And it was kind of, I can really imagine it as an autonomous sort of education element that can really work without a human babysitter, so to speak. It'll be interesting to see how that works out. Let's see. Atma comments. Most AI algorithms are going old and useless, and these algorithms need updates as the business systems need upgrades, as business clients need changes. Any comments on industry's pathway to adapting AI? You know, there are these trends that wash through the sort of the IT industry. 1980s, everything had to be an expert system. Later 1980s, everything had to be object-oriented programming. Later on, you know, all these different kinds of trends. Then there's the cloud, then there's blockchain, then there's modern AI. What's interesting is these things always build up a kind of hype wave that goes higher than it should. But they always leave a residue that's pretty interesting. And to me, kind of the rethinking of systems that those, you know, the hype wave gets everybody alert. Oh my gosh, we should be thinking about this. The result is that some systems that are often built decades ago, finally somebody gets the kick to really update that system. You know, for example, blockchain with transaction systems, it gave a kick to modernize transactions. This didn't work completely, but it gave a kick to do that. And similarly, the cloud was sort of, well, it was a return to earlier eras of kind of centralized computing. But again, it gave a kick to rethink what can one do if computing is centralized. And so I think that's, you know, what we're seeing with AI is it's a kick to rethink things. Now, what we've seen is, well, an awful lot of people coming to us very confused about what AI might do for their businesses. And actually, one of the things we've been really emphasizing through our solutions team is AI strategy and prototyping. Like, you have a business and it does these kinds of things. How can AI actually help you? Not the hype, but how can it actually help you? And the great thing that we're able to do is, because of our technology stack, we're able to build an actual example as part of sort of a proof of concept consulting engagement. We can actually build a real example that people can go show to their boards and so on and say, this is what we could actually do with AI. It may not be in the first effort. It won't be the full production system. That's a bigger project. But it's something where we can, because of the technology we have, we are in a unique position to prototype what AI can do. But it's also important that we as a company have learned a lot about that, and I think have pretty good intuition about what's going to work and what's not. I mean, one of my rules of thumb is if 80% success is a win, you can use machine learning. If you need 100% success, don't try using machine learning. If you want, you know, if you're saying I'm going to rank a bunch of things, and yeah, you know, most of the time we want to rank the good stuff high, that's a good machine learning use case. If you want to say I'm going to do this precision computation, forget it. Use actual computation to do that. And, you know, there are heuristics like that you can apply. But I think it's been something where we're sort of in this unique position to really be able to try out AI in different cases. And I think and I think, you know, we saw an early kind of wave of hype in 2023, and a lot of people like, we need to do AI for something, but we have no idea what it is. And I think we're now seeing a slightly more sober kind of version of that. And you know, I think one of the things that we can offer as a company is this strategy and prototyping capability, which I think we're going to, you know, we do really well at. You know, I have to say, in terms of understanding AI, back in February of last year, you know, so many people had asked me, how does ChatGPT work? Why is it possible? That I sat down for basically a week and I wrote a piece about that, which turned into my little book about ChatGPT, which has been shockingly widely read by an awful lot of people, a lot of sort of industry leader type people, including a lot of people who were the creators of the technology. And I'm like, oh my gosh, you know, did I get it right? And they say, well, we don't really understand how it works, actually. And, you know, your sort of high-level description was as good as it gets. So that was sort of an interesting thing, a little bit. You know, I write a lot, as many of you will know, and that was something that I wrote quickly, and it's taken a lot longer to write a lot of other things, and yet the thing I wrote quickly seemed to be a thing that was very widely read. But that's what happens when you're writing kind of something that timely. Ben Manring says, how about, this is referring to AI safety, I think. What about keeping AIs from spending money? Not perfect, but potentially a strong limitation on their ability to get out of control. I'm sorry to say, AI spend money every day, all the time. The ad bidding markets are full of AI spending money. The quant hedge funds are full of AI spending money. Even increasingly as people use kind of agents, software agents, to buy their plane tickets and things, AIs are spending money. I think that story is if the AIs want to go out of control and spending money, and when I say want to go out of control, that's a weird anthropomorphic projection onto AI. But we're past the point of no return of AIs being deeply connected to the financial system and so on. And in the past, we've seen even with pre-modern AI, program trading of making trading decisions based on signals with automated systems has led to all kinds of issues. I mean, there are times when the market has basically gone unstable as a result of program trading, and there are all these ways the market's shut down when things happen, and to try and sort of deal with the fact that program trading was doing things which were sort of too simple to the market, and then one can detect that and sort of shut it down. But the insidious sort of AI infiltration of the market, well, that's kind of like what our friends in the quantitative finance business, that's kind of what they do for a living. Let's see, at Sushi, using gradient information for parameter optimization, known as steepest descent, presupposes analytical regularity in the brain's learning process from a mathematical perspective. Why is this assumption in neural nets justified? What guarantee is there that the mathematical expressions of information processing in biological systems are analytic or regular? Yeah, there's absolutely none. I mean, that's why I found it really interesting that we were able to get a long way just using bitwise machine learning, where what happens is you just have an array, and at every place in the array, you pick one of two Boolean functions, like let's say AND or XOR. And just by rearranging that array, you can learn all kinds of functions. And actually, one of the things that's interesting, one of the big things that people have felt really launched the neural net revolution of current times is the backpropagation algorithm, where you're essentially using, neural nets make a composition of functions. And if you say, oh, neural net, you got the thing wrong by this amount, okay, backpropagate that error into the weights that determine those functions in this chain of functions. Well, there's a way of doing that using the chain rule. It's sort of big application of calculus. And there's a unique way when you have infinitesimals of backpropagating that error using to say how you should change the weights. Well, in the case of discrete systems of the kind I was just looking at, you can do forward mutation. You can just say, flip a bit, see what happens. Does that improve things or make things worse? Flip another bit. Does it make it better or worse? You do forward mutation. Well, you might say that's terribly inefficient. Why don't you do backpropagation? Well, you actually can do backpropagation because there's a Boolean analog of differentiation. So you can do the exact same thing of a sort of chain rule for Boolean differentiation. The only thing is that unlike in the case of ordinary chain rule, infinitesimals have this nice feature that two of them is like one of them, so to speak. So you kind of don't have to account for whether you had two infinitesimals or just one. In the case of Boolean functions, you don't have a unique inversion of the chain of function compositions. You have many paths, a multi-way system of different inversions. But it looks as if, in the end, forward mutation and following a few paths are pretty much equivalent in the computational effort that it takes. And none of those things show continuity. I mean, they don't have that explicit form of continuity. Whether the, I mean, it's really an interesting question. We were talking earlier, I was talking to Sebastian Mazzera, one of our Innovator Award winners, and his work on the S matrix of making a kind of neural net in the middle of the S matrix. And there's sort of a question of the analyticity properties of the S matrix and how could those be inherited or not by analyticity properties of neural nets. That's kind of forcing analyticity into, or wanting analyticity in the neural nets. But, is thinking analytic, and does it have steepest descent? Oh, I doubt it. And I think the fact that these fully discrete neural net analogs are as analogous in their behavior to neural nets with continuous weights and so on is interesting, and a sign that it just doesn't matter. That essentially what I call the principle of computational equivalence is a strong enough principle that across these systems of very different architecture, you can still get kind of the same computational capabilities. Let's see. Gosh, many of I know I should stop fairly soon. James Wiles from our Wolfram Institute is asking, there was a question earlier apparently about physics being fundamentally computational versus being based on laws of physics. How does the physics project hope to make progress in the field of physics by taking a new approach? Well, gosh, this is a long story. I mean, our physics project kind of starts from something that, kind of people assumed 100 and something years ago and then couldn't quite make work and so gave up on, which is the idea that space, like matter, like photons, is discrete. And it turns out that the kind of limit of this sort of discrete hypergraph rewriting thing, just like the limit of molecular dynamics is fluid dynamics, the limit of discrete hypergraph rewriting is the Einstein equations, plus it seems the path integral and quantum mechanics. And so that's kind of a big deal and kind of a sign that one's really on the right track, because from so little one gets so much. The question of sort of laws of physics and what laws of physics will, the thing that I think is a really big deal is being able to derive the laws of physics, not just find the laws of physics, but really derive the laws of physics from the characteristics of us as observers, from very general characteristics of us as observers, derive those laws of physics from underlying computational principles. And that's, as far as I'm concerned, a big success story. We will no doubt derive other laws of physics that we didn't know already, and we have some indications of what those are, although we need help in kind of getting the experimental, in working on the one side from this very low-level machine code, on the other side from what's known in experimental physics, and kind of merging those together to find kind of places where we can, for example, see the discreteness of space. What will be our analog of Brownian motion, where we get to see that space is really discrete, as Brownian motion showed that matter is really discrete. And it's kind of like we look at things with black holes, we look at some things like that. My current best candidate, which just needs a lot of working out, well, actually, one thing that's very scale independent, because one of the issues is we don't know the elementary length. People with molecules at the turn of the 20th century were really lucky that molecules are big enough to see their effects with microscopes in Brownian motion. But we don't know if the discreteness scale for space is big enough that with any kind of current experimental apparatus, we can detect it. But there are effects that are scale independent. For example, one of them is dimension fluctuations, where the dimensionality of space is not precisely 3, but has some variation from that. And the expectation is that there will be utterly bizarre forms of gravitational lensing that happen when photons propagate through regions of fractional dimensional space. But there's a big stack of mathematics and mathematical physics that has to be built to see exactly how that works. But then my most ironic, I suppose, implication is probably what happens, what is the overall residue of all of that detailed action at the level of discreteness of space? Well, in the case of matter, we know that the sort of residue, the macroscopic residue of all of that activity on the scale of molecules is heat. Back in the early part of the 19th century, people said, well, heat flows. Anything that flows must be a fluid, so we'll invent caloric fluid to represent heat. But heat turned out to be the microscopic motion of molecules. Well, similarly, it is my suspicion that dark matter isn't matter at all. Its name is misleading, as caloric fluid's name was misleading. But rather, it is some macroscopic manifestation of what I've been sort of calling space-time heat. We'll see if that's the case. But that's an interesting possibility of something where we'll be able to make a connection between something very microscopic and something measurable. I also have a suspicion that in quantum computers, that the most interesting thing that will come out is a fundamental physics associated with the noise in quantum computers. I think my analogy is that, you might think we were trying to build a quantum computer, we're getting rid of the noise. It's an engineering problem. It's like we're trying to build a telescope. We want the telescope to work better and better. Eventually, we're going to see a grain of sand on Mars, but we're going to get that by polishing the mirror better and better and better. But the truth is, you won't get that because of the diffraction limit on telescopes. And the question is, what's the analogous effect in quantum computing? My guess is there is an analogous effect. My guess is that it's related to the maximum entanglement speed that you see in our models. And very nicely, if you know the maximum entanglement speed, then there's a direct conversion that gets you to the elementary length. So probing the noise of quantum computers may be a way, if the engineering has been done well enough that noise is truly a noise floor that's associated with physics, not a noise floor associated with engineering, then we might be able to deduce the maximum entanglement speed, and that will give us the elementary length, et cetera, et cetera, et cetera. And sort of it's one of my hopes that if you really literally could collect all the data, which people tend to not give because they just think it's their imperfection that there's noise in these systems, you could really get all that data and organize it properly, that you would be able to see, you plot all the points, you'd be able to see, gosh, there's some fundamental phenomenon here, and that fundamental phenomenon, I suspect, is associated with maximum entanglement speed, and it will be really exciting if that was measurable. Let's see. Zhigang Hang says, it's quite long here. The recent advancement of robust adaptive control promises that one can learn almost anything that has a parametric dynamic model, and further control of the system relative degree is relatively small, like up to 4 or so. The computational complexity of the controller is so great that for 20-state systems with relative degree 2 or 3, the controller runs to 10 gigabytes of data. The computation of the controller is relatively easy, but the simulation for closed group systems takes a long time since the nonlinear function is too complicated to compute. What do you see that one could do to speed up that computation process? Well, neural nets might be your friends. It really depends on the structure of that function. Is it the case that that function has sort of the smoothness properties that we don't understand very well for neural nets, but the smoothness kinds of properties that neural nets can capture, or is it full of weird singularities and cusps and so on that that they can't capture? And I think we can't know that. I mean, we tried experiments a decade ago on making control systems with neural nets, and they worked okay. I don't know whether we pushed them hard into nonlinear regimes and so on, but they sort of seem to work okay. And that seems like the path forward. Now, it has to be said that it's a sort of bizarre quirk of history that feedback control has developed its own methodology and so on. Meanwhile, reinforcement learning has developed its own methodology. And there's sort of each field has developed its own words for things, but they're kind of doing the same thing. And reinforcement learning kind of plays through neural nets a lot. Feedback control tends to play through much more sort of mathematically defined systems. So I think there's sort of a connection to be made between those things. Let's see. Mohammed asks, how many server resources, cores, RAM, storage, does Wolfram Cloud and Wolfram Alpha use? Boy, I don't know the answer to that anymore. I certainly used to know. I mean, it's a bunch of racks of computers sitting in several data centers. I mean, I don't think I can really answer that right now. It's running, let me think. See that. 100 QPS times yeah, I mean, it's thousands to tens of thousands is a typical moment of use, but it really varies a lot. And I can't answer that in a useful way immediately. Actually, it's about to change because both the Wolfram Cloud and Wolfram Alpha are getting fully containerized. And so that changes the profile of usage. I mean, normally for example, we will be routinely running foreign language versions of Wolfram Alpha in bringing up containers, bringing down containers to fill in as the sun goes around the earth, so to speak. So we're running the Japanese version during the night on the same, on containers on the same physical hardware that we were running English language versions during the day and so on. So we get to follow the sun as we tear down and set up containers and such like. Mohammed is saying, excited for tabular functionality. If done right, could really open things up. I think we've done it right. I think it's really very good and very efficient, and kind of leverages sort of all the latest technologies for making that work. So I'm pretty bullish about how that's going to play out. Matt is asking, is computational irreducibility different from the idea of undecidability in mathematics? The relation is more or less this. Computational irreducibility is about sort of the ongoing doing of a computation. Undecidability is about what's going to happen in the end. So if you have a computationally irreducible thing and you ask the question, what's the infinite time behavior? That will be a question about which there is undecidability. And systems that have undecidability are systems that have computational irreducibility, but undecidability is kind of the infinite time version. And it's less, there's a lot more that's important in the practical doing of science and technology and so on from computational irreducibility than from undecidability as such. So that's kind of the relationship between those two things. And there's questions about, the relationship between computational universality and undecidability. Those two are also sort of equivalent kinds of issues in the end. There's some kind of tiny sliver of possibility that they're not equivalent, but I think that they are. And that's kind of the story of that. Mohammed is asking, can you give some key differences between computational thinking and traditional mathematical thinking? Yeah, I mean, I think mathematical thinking is about, can you write a formula? Can you write an equation? Can you describe things using the methods of calculus and so on? Computational thinking is there a computational way of describing that using programs, using rules that you can describe computationally? So there are all these questions. The building blocks that you have in computational thinking are very different building blocks. In mathematical thinking, your building blocks are multiplication, exponentials, differential equations, things like that. In computational thinking, your building blocks are things like image processing, geographic data, things about sort of algorithms for pathfinding, things of that kind. So it's a different set of raw materials that you learn to put together rather than the raw materials specifically of mathematics that have been convenient, particularly in times when we didn't have computers to help us. Ray is asking, do you think that LLM embeddings are going to be more or less useful in the future? I assume LLM embeddings, you mean kind of getting vectors out from an LLM and doing things like vector databases and so on. You know, embeddings from LLMs are a very weird idea because it's kind of a sense of a linear sort of vector space type thing that is coming out of things like knowledge and so on. The fact that anything like that works is interesting. I think it's a sign that sort of anything works. And I think what's happening is that in vector databases, in the end, you've got these vectors out. In the end, how do you tell what's close? Well, you just literally measure closeness by some cosine difference or dissimilarity or something like that. I don't know. I mean, I think that embeddings have taken us further than we might have expected them to. And so I would kind of expect that they'll go on being useful. In the end, there may be, this question of what's near. An alternative approach is the approach that's more used in kind of a classifier where you're going, go to the attractor. Are you close to this thing? Build the attractor, custom build the attractor, as opposed to kind of pre-compute this way of computing embeddings and then just use distance in the embedding space. But I'm not sure how that's going to play out. Jonathan Miller, I certainly understood the rationale for the end of print editions of Mathematica with Mathematica 5, but when they went away, I lost access to coherent, comprehensive overview and drill down. I've been thinking for years about a table of contents for the documentation and asking about that. Well, you know, I see our guide pages as kind of the table of contents, really. You know, you start from the root guide page and then you're drilling down and drilling down. And that's kind of intended to give one sort of a table of contents type view of the different parts of the system. You know, I wrote that little book, Elementary Introduction to Wolfram Language. It's a good template. People can use it. Some other people have written books, but I encourage people to write other introductions to Wolfram language. The one that I wrote, I had the sort of constraint that I wanted it to be readable by high school students, and it involves no math. It doesn't involve the idea of a function of a variable x. So there are no plots in it, only list plots. There really should be other books, and there are. There's a lot of other books, including many people here have written books, but there's even more that can be done in providing kind of these overviews of the system. Now, the version 1 book, 600 pages long, it was, I think, the system was small enough that it was easy to give a coherent view. At this point, the principles of the system are small enough you can give a coherent view, but the full scope of the system is just ridiculously huge by the standards of books. It will be a multi-100,000-page book. The question of what you can explain about the principles, here's the challenge. The challenge is that explaining the raw principles without sort of building up to them by showing examples is pretty hard for most people to understand. Some people who think very formally, you can just give them a principle and they can run with it. But most people, including people who ultimately are capable of thinking pretty formally, you really have to build up to it by giving examples and so on. And I think that's, you know, it's an effort to do that. Now, in the thing I'm trying to write about computational thinking, I'm going to try and do some of that. I hope to be able to build up to the principles. And once you understand those principles, you have sort of a bigger view of the system. But yes, it's an interesting challenge. And, you know, as I say, guide pages are our effort to provide something like that table of contents. But it's an interesting challenge to see, you know, and again, I tried it back in 2016 with the first edition of Elementary Introduction to Wolfram Language. I found that quite interesting to write. I wrote it very quickly, but it was interesting to write because it's kind of this, I sort of intended it to, how do you make a series of chapters that build on each other? Gosh, we can't talk about sound until we talked about strings because we're using strings to describe notes and so on. I was a little disappointed to discover many people teach with that book, and I was a little disappointed to discover that all the effort that I spent in making the sections build successively on each other, many people use that book by taking, you know, by taking it in a different order than I had written it in, and they managed to make that work. And it's kind of like that is somewhat informative for the new thing I'm writing, where that won't necessarily, but where I won't spend so much effort threading the pieces through in that kind of way. Andrew DeYoung asks, just curious, do you have any non-science, non-research hobbies? I suppose my main hobby is educational kinds of things. I've been interested in actually sort of doing education with kids and so on. Yes, it's usually talking about, well, maybe sciencey kinds of things, but that's a hobby of mine. Another hobby has been, well, I suppose it counts as research and science, but has been history and trying to understand things about the history, intellectual history, and so on. But other than that, I'm pretty hobbyless, I think. I for years tried to see one mainstream movie per week. I don't watch television or anything like that. I don't think I would have any time to do anything if I did that. But that's become very difficult in recent times because mainstream movies are pretty sparse at this point. But that was sort of something, sort of a hobby. And I always realized the difference between, you know, I've been involved a few times in movies and the making of them, and it's such a different experience. You sit and watch the thing, and it's sort of relaxing relative to knowing how the sausage is made, so to speak. And I realized that a lot of things I do where we put a lot of effort into making the sausage, but then for many people who are consuming it, it really is, while for me, there's a big focus on how it's made, for other people, it's really just like, let's have the thing to eat type thing. Andrew also asks, how do I convince a supervisor? He says, Mathematica is so much computationally slower than Python, C, or Fortran. Really? Doing what? I mean, I think you know, one of the things about Wolfram language is that sort of the goal is, what are the lumps of computational work that people want to do? Let's implement them. They become functions. We make those functions as efficient as possible. And because we have access to much higher level capabilities, we can make those things even more efficient than anybody could imagine making them before. You know, you think you're doing a numerical integral, but actually let's say it's a multidimensional one. Actually, you have to do some computational geometry. Maybe you have to do some algebraic computation to smooth out singularities. For us, being able to do that algebraic computation, being able to do that computational geometry, maybe being able to do some graph theory in there, that's free because we have this kind of integrated system that has all those capabilities. But if somebody was making, I'm going to make a library for doing numerical integration, it's going to be the best in the world. No, you're not, because doing that from scratch, from the sand up, is much more difficult, almost impossible, relative to doing it, making use of all of the kind of capabilities that we have immediate access to in Wolfram language. Now, one of the things that's been interesting is if you write Fortran-like code in Wolfram language, how fast does it run? That's not what we've optimized for. We've optimized for people writing code where it's using the lumps of computational work that we think are useful and that we think are the right things to use, and building functional programs and so on. And turns out it's really efficient doing that. But if you write Fortran-like code, well, actually, then you can use our compiler. And the new compiler does very well on that kind of low-level code. That code is very easy to turn into a kind of low-level. I mean, we're turning it into something that's actually comparable to C, probably more efficient than C in most cases. It's directly turning into machine code. So if you're writing kind of things that you might write in Fortran, I mean, good luck writing something that does some elaborate form of numerical, symbolic solution to differential equations in Fortran. You're not going to do that in Fortran. You have something you're going to write in Fortran with loops and so on. Well, if you write the same thing in Wolfram language and compile it, I suspect you'll get something that's certainly comparable to and probably faster than what you get by doing that same thing in Fortran. And that's sort of the opportunity in Wolfram language is you get to do all these different things and fit them together, but also the very core algorithms can be better and faster because they get to make use of the rest of the system. And if you really want to write very low-level code, well, increasingly the compiler is able to take that and make it sort of machine code efficient, so to speak. So I think that's kind of the story. And I feel very good about the fact that for the things that I'm doing most of the time, it's really kind of the pure Wolfram language is very efficient. Occasionally, I'll have something where I want to go to the effort to compile it. And sometimes that takes a bunch of hints to the compiler, sort of me really figuring out, well, I don't really care about that case where the thing might be a zero-length list or whatever else. I'm going to exclude that case and make my computations that way. But that's been sort of my workflow, at least. A question, somebody from our team is commenting about the question about hobbies, saying, honestly, humans are your hobby, from kids to CEOs and all the way in between, as demonstrated in the massive overrun that I did in Meet and Greet. Yes, Danielle is right about that. Actually, I forgot that hobby. Okay, thank you for that prompt. I mean, yes, I sort of have a hobby of mentoring two categories of people, CEOs and kids. Those categories of people have one very important thing in common, which is they both tend to believe that anything is possible. I'm an advisor to many companies, and it's sort of a CEO counseling function, I suppose. I find that quite interesting, and I think I've been very helpful over the years. Yes, that's a hobby of mine. I suppose another hobby that I've been I'm always curious about lots of kinds of things. I like to understand different areas. I suppose amateur medical diagnosis has been another hobby of mine, which I just find it interesting. It's one of these things where it's sort of a diagnosis of things I find interesting. When diagnosis of complicated computer systems, medical diagnosis, they're similar kinds of problems. They're sort of knowledge meets judgment kinds of things. And I have to say, I don't know whether it's quite a hobby, but when we have operational problems with computer systems, kind of the folks who are dealing with that and do a great job are kind of not usually in the CEO orbit of most companies. And I kind of have the principle, if things have gone wrong and we don't know how to fix it and people haven't been fixing it, but I'll kind of dive into the trenches and try and see whether I can figure out what the networking issue is or whatever else. And I find that interesting. You know, I found that problem-solving skills that I've learned in quite different areas end up being really pretty useful. I would say the number one principle about debugging in that kind of case is do Wolfram language analysis. Take those log files, and instead of eyeballing, do we see any weird errors, just read the thing into Wolfram language and start doing analysis on it and see what regularities you can see. That's sort of the number one thing. Plus, the other thing is, it's always interesting in both computer diagnosis and medical diagnosis, is like you have these different probabilities of different things that might be wrong, and you have to kind of know how to navigate sort of, as you try different hypotheses, try to navigate sort of which hypothesis is really the most plausible. And you have to learn a certain brutality to your own hypotheses, so to speak. That's, you know, one of the very common mistakes in both kinds of diagnosis is you've got 5 things that might be going wrong. At the beginning, you exclude one of them because you do some test and no, it doesn't pan out that way. So you say, that can't be it. You go on, you go on, you go on. Eventually, you know, you've pretty much excluded almost everything, but you forget to go back to that thing that you excluded at the beginning, where you had, you know, probably a certain probability of a false negative or whatever else of the test you did. And but you just forget that because you're drilling down into the things that are the things that you're pretty sure are the things that are going on because you already excluded that other thing. And I think that's an important, I mean, to me, that's an interesting discipline of thinking, to kind of know how to sort of reject that hypothesis that you had. You know, I think in doing science, one of the things that's been I would say one of the bigger challenges of doing science is to kind of have a theory but not believe it too much, and to be prepared to let the chips fall as they will. And you know, you do experiments, and for me, I'm constantly humbled by doing experiments in the computational universe. My sort of common statement is the computational animals are always smarter than we are. Just happened to me, even today. It's like something where I can't believe it does this. You can do this with this kind of computational system, and by golly, it finds a way that I didn't guess. And it's always a thing that it's kind of a very, it's sort of an important intuitional thing, that it's sort of a story of computational irreducibility, but it's also a story of sort of the unexpected can always happen. And it's kind of an interesting piece of psychology to get to the point where you're doing these things and it's like the chips are going to fall where they fall, and you kind of have to be sort of okay with that. And I suppose it's the good thing that's happened to me, at least, is that I feel like I've kind of I'm going to try different things, and I have pretty good intuition these days. Things usually work the way I expect, but they don't always. But that's okay. I feel like that's a positive for me because I'm learning something new from that experience. Let's see. Okay, probably our last question for the night from Antonov. to what degree do you use category theory in the physics project? Is it used for descriptive purposes or for discovery, say by analogy? There have been a number of people who've been very big on using category theory in the physics project. I would say that some things have been useful for sort of characterizing what's going on, particularly as we get towards the Roolead. That's closely related to the infinity groupoid, which is sort of a limit of higher category theory. What we've learned from that is not completely clear yet. I think that I haven't been sort of on the leading edge of using category theory in the physics project. Let me say something about category theory. So I think category theory is actually a very interesting general characterization of a small subset of all computation. And that small subset, I think, is the computationally reducible computations. See, here's the thing. In category theory, you have a morphism, F and a morphism G. And then one of the axioms of category theory is if there's morphisms F and G, there's another morphism F composed G. Well, that assumption that there's always the jump morphism, that's that composition, that assumption is an assumption that, in a sense, you're not sort of adding up computational effort. It's not like F is a bunch of irreducible computation, so's G, and so that's even more computation to do F composed G. It's sort of an assumption that there's computational reducibility and that you can kind of do that composed morphism with sort of not outrageously more effort. So in some sense, maybe category theory is the general description of a certain, at least some class of computationally reducible computations. So it won't capture everything, but it captures certain kinds of things that maybe are a good match for the kinds of things that we humans kind of latch onto in thinking about mathematics. And I think, a thing that we've been interested, there's a pretty good package now for doing category theory categorica in Wolfram language. Actually, I think there are several packages in Wolfram language for doing category theory. I know one that's in the function repository is categorica. There's sort of interesting questions about, is it useful to think about Wolfram language in category theory terms? I think the big test is functors, whether you can go from one function in Wolfram language to another function, whether you can have a functor that goes from one function to another, which sort of translates from one function to another. And we don't really know how to do that yet. And that's sort of an interesting and challenging thing. And I think, if that's cracked, then I think that really opens up a lot of sort of the fanciness of category theory to really thinking about Wolfram language in practice. I would say that some of the frontiers of what we're thinking about are things where, in Wolfram language, expressions are tree-structured things. There's the question of what is it like when they're hypergraphs? What is it like when they're DAGs, directed acyclic graphs, rather than expressions? Now, we do have DAGs because every time you define a variable, you're kind of merging things into that variable. It's sort of a common sub-expression kind of thing. But what does it really look like when? What does it look like when you do those things? What does it look like when you have a multi-way kind of computation and you're kind of tracking these different paths of computation and so on? These are things that we're sort of actively thinking about, and that I hope we will be able to kind of unscramble to the point where we can really make them understandable in the language. And maybe category theory will be helpful there. I consider that a possibility, though not a certainty. All right. Well, I think with that, we should probably wrap up. And I hope people have been having a good time at our conference. And I know we've been having a large number of parallel talks talking of parallelism, and lots of interesting things, and lots of interesting things that people have been talking about doing with our technology. Just great to see all these things, and look forward to seeing more. And don't forget to tell us what you're doing, and don't forget to kind of tell the world what you're doing. People will be interested. Well, thanks for joining me and joining us, the conference. And I think tomorrow I get to see a few more people in at least virtually like this. And we're looking forward to many other opportunities to interact and perhaps some physically in person and so on. So thanks a lot, and bye for now.